Hi everyone, thank you for joining this webinar. This webinar's title is Simulating a Torque Ripple for Motor Control System Design. My name is Ryoko. I'm a Motor Design Application Development Engineer from the PowerSys. PowerSys is a solution provider company for EM system design around the JMAG software. My expertise is in the magnetic simulation programs, and my base is in the Detroit area.
Hi everyone, my name is Shangchuan Li. I'm a senior application engineer at MathWorks with a focus on motor control and powertronics. I've been with MathWorks over 4 years now, with a focus on supporting customers on the industrial automation and machinery. So in this webinar, Yoko and I will show you how to simulate torque ripple high-fidelity motor model in Simulink. And specifically, we will show you a workflow to integrate FEM JMAG motor data into Simscape Electrical. So in this project, Yoko is focused on machine design, component level simulation by generating high-fidelity FEA motor data. After she performs FEA analysis, then she will pass the data, the FEA data to me, and as a motor control engineer, I will work on system-level simulations to validate torque controls in Simulink.
So here's today's agenda. First, we will talk about why we do this webinar, and then here we will talk about the impact that torque ripples brings to the motor drive systems. Then we will talk about modeling the torque ripple for motor control design. Here we discuss how we can integrate the lookup table file from the FEA into the system-level simulation like MATLAB Simulink. Then, afterward, we demonstrate how we can implement a control strategy to mitigate torque ripple using a motor plant model with spatial information from the FEA. And then, at the end, we will summarize our discussion.
So what is torque ripples? So torque ripple is a dynamic part of a torque on top of a steady state condition. So imagine we have a low torque applied to an electric motor, where in this case, we see a torque has this frequency and amplitude to this given torque of 2 Nm. In an ideal world, we are expecting to see an average value of torque output, but in reality, what we see this is a periodic peaks and valleys around these DC values. So that's why we consider these torque ripples. So when we talk with our customers across industries, how to deal with torque ripple is really critical. In robotics applications, a smooth motion is always critical. So it's all about precise position control. But if we have a torque ripple, it will make the inaccurate position control and further impact the overall transmission line or conveyor control. And on the other hand, for the automotive industry now moving towards more electrifications, and it's more than ever important to analyze NVH, which is noise, vibration, and hardness. And we know that permanent magnet synchronized motor are continue to be the most dominant electric motors in electric vehicles. So, but its inherent issue is the cogging torque. High cogging torque can cause a significant torque ripple during all kinds of, speed operation. So these are the impact of the torque ripple in many applications.
Thank you, Shangchuan. So then you may wonder what is the source of those torque ripples. As for the source of the torque ripple, there are two major components. One is slot geometry, and another is magnetic saturation. The first one, slot geometry, is caused by the interaction between this magnet and slot. As the rotor rotates, the rotor magnet will be pulled to the stator at the stator tooth. But at the slot openings, the magnet is not pulled by the stator iron, and this change of the pulling force generates the torque ripple. The second source is magnetic saturation. The current waveform can be distorted due to the magnetic saturation when the motor is driven by the voltage inverter. And then this distorted current contributes to create unwanted harmonic torque components. So now we reviewed why torque ripple is a problem and what is the source of the torque ripple. Then next question would be, how can we consider the torque ripples in a motor control design phase? As we already discussed, torque ripple is dependent on motor geometry. It means even if the machines have the same number of the poles, ripple profile will be different. And then here I am showing that the two different motor geometries. So these motors both have the same number of poles, 4. However, as you see, the torque ripples created from each motor are different. So just having that parameter of the motor doesn't help us to understand how the torque ripple profile will be. However, the traditional constant parameter model does not represent the geometry information. So here I am showing that constant parameter model traditionally used on the left side. So this equation does not include that information of the rotor position theta. Therefore, what we can derive from this constant parameter model is just a flat line without having any ripples. So to be able to capture the ripple, plant model need to have the rotor position information as shown in the right side of this slide's equation. And then this lookup table of parameter model with spatial information have that information of the theta as the input parameter. Therefore, it can represent that these torque ripples up and down on the torque.
So as Yoko mentions, we are going to show you in this presentation is to show you how to capture the torque ripples through JMAG tools and how to simulate the behavior of the torque in Simulink and design motor control algorithms to tackle the torque ripples.
To talk about the plant models with spatial information, I want to start with the introduction of the JMAG. JMAG is a FEA, finite element analysis package software for motor design and drive system design. It has a wide coverage of solutions around the electromagnetic design. In this slide, the first one left is the analytical model solution from the JMAG. And next is the detailed design with the FEA, which is the core of the JMAG technology. And the last one is a solution for the system-level simulation, like MATLAB Simulink. JMAG can link with the system-level simulation tools, providing the high-fidelity plant models to them. And this solution is called JMAG RT. Basically, JMAG RT is a lookup table of motor parameters, which are pre-calculated by JMAG FEA. And following the operating points are defined by the user, JMAG runs a parametric analysis of the FEA and consolidate that FEA result into a lookup table. That is a JMAG RT lookup table. Now, one of the questions I get often is, what is inside in the JMAG RT model? So here's a quick summary of the JMAG RT lookup tables. Basically, these lookup tables inputs are current vector amplitude, advance angle, and rotor position. Outputs are total flux, inductance, torque, and iron losses. When referring to iron losses, the rotor speed is used instead of the rotor position.
So as Yoko mentioned, JMAG RT can create lookup table for modeling high-fidelity motor model. So how do we integrate a lookup table with Simulink? So here we provide you a 3 framework to use JMAG RT with Simscape Electrical. And these 3 framework all use lookup table from JMAG RT, but we support different type of solvers and interfaces that you can choose from. The first approach is use FEM parameterized block. And under this approach, you will use the Simscape solver and Simscape interface to simulate your motor control system. And second and third is based on JMAG RTS function block. And one is to use network coupler blocks, and the other is directly connect with Simscape terminals. So it really depends on your use case and level of fidelity of modeling high-frequency machine losses. You can choose which framework works best for you. Now I'm passed to Yoko. She will talk about how to create a FEA motor model.
Okay, Chandra. So to get motor models, first thing first, we need a spec. And for this webinar, we borrow a spec sheet from our literature. And when using a JMAG, we can get a motor geometry from this constant parameter data spec sheet very easily. So what we need to do is first open this tool called JMAG Express, then fill the box with the values from the spec sheet, like a number of the slots, number of the poles, rotor dimension, stator diameter. And then you can get good geometry model that can be plugged into the FEA model, like this one. And then once you get the geometry model, you can export this geometry into JMAG Designer and can create a mesh model with one click. And you get these mesh models. And once we get the geometry model, then next is a setup the lookup table generation. For this, we use a tool called JMAG RT Library Manager. In this tool, first, we input the geometry model file. So here we selected a PMS model and then set that mesh model here. Then next is that filling that node section, giving basic information of that this motor configuration. Then we move to that defining that motor sampling points. Here we set that current, advance angle, and rotor position. So also we set that speed for the iron loss tables. Now we are setting the iron loss table here, and then specifying the maximum speed. Then pretty much done. The rest is parallel computation settings, like a number of cores. And so you can choose this number according to your calculation environment. Then afterwards, just go back to the top menu and start the calculation. After the calculation done, you will get the motor model that we call RTT file from this menu. Then RTT file generation is done. Once you get RTT file, you are ready to link with MATLAB Simulink. There are multiple ways to link with the MATLAB Simulink, as Shantran was mentioning. And then depending on the block you choose from those 3 blocks, the steps are slightly different. And then this slide, first, I show that how to prepare the data for that FEM parameterized block. And in this case, since FEM parameterized block doesn't accept the RTT file directly, I mean, they accept that .mat file only. So we need to convert RTT file into the mat file. Then for that, we use a tool called JMAG RT Viewer. So first open the JMAG RT Viewer and then set .rtt file path in that this tool's GUI. Then you will get the mat file. The convert happens automatically. And once you get this mat file, you will pass that this mat file to the, your control design friend.
So once I receive the data from Yoko, then I can easily parameterize these parameters on Simscape Electrical motor block. So here we are importing lookup table of flux, torque, advance angle, and rotor angle. These are important informations to capture torque repos for modeling spatial harmonics and nonlinearities. So the next step is how can we characterize the FEM PMSM block in Simulink? So in this case, we give a 3-phase voltage source of 60 volts to the motor and a constant speed of 500 RPM. And then we can measure 3-phase currents and torque. And in order to further validate these blocks, Yoko, can you tell us how do you run the model validation in Simulink?
Question, Karen. Okay, so for this validation, I prepared FEA model from the same geometry model that I created the JMAG model in a previous slide. And this FEA model has the 8,000 elements, and JMAG model has a 12-point data in a current and 73 data points in advance angle and 121 points in a rotor position. The calculation time to create this JMAG model was 1 hour 20 minutes. And then the objective of this simulation is to validate of the lookup table model in comparison with FEA. Therefore, we use very simple input settings, three-phase sinusoidal voltage, direct input, and constant speed, so that we don't have to worry about the other components effect, like inverter switching, etc. And then, so in this slide, the bottom is the comparison of the FEA and JMAG Simscape block. The left is a current, and then the right is a torque. The solid line is FEA, and the dashed line is a JMAG Simscape. As you see, they overlap each other quite well. Also, we can see that JMAG Simscape is capturing the torque ripple in the same manner with FEA from the right side torque comparison chart. So this way, we can validate the lookup table model we created is close enough to the FEA model.
Thank you, Yoko. So the next step is how do we implement FOC torque control with high-fidelity motor model? So here is the black field orientation control architecture. So here we see, like on the right-hand side, we have our physical system of our three-phase inverter to drive the motor. And here we got the PMSN high-fidelity motor model, already modeled in Simscape Electrical block. So our goal here is to use FOC to control the torque. So in FOC, we know that we have two PID control loops to manipulate the Q-axis and D-axis currents, right? And since we are doing the SPM motor, primary Q-axis is dominate the torque output. So we also got the DQ to alpha beta transformation and also SVPWM generator to control the duty cycles for three-phase two-level inverter. So now let's take a look on the Simulink implementation of torque control. So here we have this FEN PMSN block, which is connected to a three-phase inverter with a supply voltage of 120 volt DC bus. And in order to measure the three-phase current, we also in place current sensors in between the power converter and motor, and so that we can monitoring the current feedback feeding to our PMSN controller, right? And the same thing for on the mechanical side, we also have a torque transducers on the rotor, so we can continuously monitor the mechanical torque load on the shaft. And since we are doing the torque control loop, and in this case, we are giving a step torque response from 5 Newton meter to 10 Newton meter. And we also have this gate signals output that is feeding to our inverters. They are the duty cycle generation pulses. So now I just quickly run the simulation, and we can see the three-phase currents and torque response on the left-hand side. And if we zoom in, we can also see the torque, the current ripples and torque ripples are captured in the simulation. These are spatial harmonics that Yoko has been mentioned in the very beginning of the slide. If you remember the equations, we including those rotor angle and advanced angle information. Yeah, and now let's take a look on this PMSN FEM parameterized blocks. And in this case, we are using flux linkage as a function of peak currents, current advance angle, and rotor angle. And these are the lookup table of flux and torque data can really be found in the MATLAB workspace. Yeah, if we double click on the table of flux, we got a matrix of flux data. And these are all coming from the JMAG RT tool. And as well as the rotor angle, we got over 121 data points. And on the controller side, here we have the FOC implementation. They are exactly the same as the previous block diagram I showed you. And we got like DQ to ABC and SVPW and inside of the field orientation control, we got the DQ reference frame to control the torque, and also since we want to do the cross coupling decoupling turn, so we also implement that algorithms in our torque control. So now we can simulate these nonlinear spatial harmonics of torque ripples. So what we see a lot of interest across industry is like to study different motor control techniques to reduce torque ripples. And just to give you an example, here we are implementing a feed-forward torque ripples. We are implementing a feed-forward torque control to reduce the torque ripple. And we can see that after this implementation, the torque ripple is reduced up to 50% compared to before the torque control. So with Simulink, the message here is we can explore and design different control strategies to see which control technique can help you mitigate torque ripple. So, and here, we also want to highlight for the second and third framework, in this case, it's basing on the using JMAG RT as function block. And with this approach, you can easily import RTT file directly to the Simulink environment without converting to .MATLAB file and parameterize the lookup table. So same thing for the JMAG RT as function blocks. So with second framework, you can also easily implement this block with the rest of the Simscape Electrical components, such as power electronics components and FOC algorithm. And now, if we double click on this JMAG RT function as function block, we can directly import lookup table from the RTT file. One thing to be different is this block is you can select the iron loss table and AC copper loss data. So these are more advanced settings for modeling loss information, and Yoko will discuss more what's the difference between these advanced iron loss and copper loss information.
Okay, so now we see all solutions can offer the spatial harmonics. Then you may wonder what is the difference between these three RT blocks. There are some differences. At this point, I'd say the biggest difference is at the loss modeling, especially the iron loss modeling. So to capture the iron loss in a system level simulation, there are a couple of the approaches, or let's say 3 approaches. And this chart tries to categorize those approaches from the point of the fidelity level. The most low fidelity level is the Steinmetz method, which is a classic approach and then most well known. Second fidelity level is a table with current and speed. This can perform relatively good accuracy unless that iron loss due to the carrier frequency is not that significant. Then the third method, that is the most accurate one, and this approach captures the carrier frequency as well, and this is called the high frequency iron loss. And then coming back to the discussion of the JMAG RT blocks, now I show that these three blocks in the y-axis of this chart, and then the FM parameterized block can support first two methods, Steinmetz and table with current and speed. And in the meantime, JMAG RTS function blocks, the network JMAG RTS function block network coupler and JMAG RTS function block with Simscape terminals. They support a table with current and speed, as well as a high-frequency iron losses. So I'd say that first block, parameterized block, supports the basic iron loss modeling that can capture the fundamental component of the iron losses. And then another two methods, JMAG RTS function block, network coupler, and Simscape terminals that are a little bit more advanced iron loss. And from the next two slides, I will show you that how significant a difference we will see when considering those high-frequency iron losses. So first, we will take a look at the comparison of this table with current and speed iron loss method. So to check the accuracy of this table with current and speed iron loss method, we prepared this simulation. 8-pole 48 slots IPMSM, and then the operating point was low speed high torque grid points, and then the carrier frequency used was 6 kHz. And with this test condition, we simulate three patterns. First is a JMAG RT with a table with current and speed iron loss, as we discussed. And then as the source of the voltage, the PWM inverter was used here. Then the second pattern is the pure FEM, not using system level tools. And then this case, the source was sinusoidal voltage. And third pattern is also the pure FEM, JMAG designer, and that PWM inverter was used as a source for this third case. Then here's accuracy comparison for the table. Here is the result of these three patterns. In this graph, we compare the JMAG RT with inverter drive, FEA with ideal sinusoidal current, and then the FEA with inverter drive. And then as you see, JMAG RT with inverter and FEA with inverter has discrepancy. And then you will easily notice that rather JMAG RT with inverter has the same losses with the FEA with the sinusoidal voltage input. Why this difference is created? It actually but makes sense when we know that the table with current and speed does not have the carrier frequency information and it just only contains the fundamental frequency information. So when we run the motors with the PWM inverters, this PWM frequency or carrier frequency will create small ripples of the current, and then that contributes to the additional iron loss. However, those effects cannot be captured when you use this iron loss method, table with current and speed, and that is the reason of this discrepancy. So here's the summary. So table current and speed method can capture the fundamental component of the iron loss, but cannot capture the iron loss due to the carrier frequency. And then let's move to the next comparison that is about high frequency iron losses. And here is an example we prepared to check the accuracy of the high frequency iron loss method. We prepared this simulation, the IPM with for the traction motor with 48 slots, and then compare this iron loss at the several operating points. And all results are calculated using 6 kHz switching frequency unless it is specifically mentioned. And for instance, this first graph is at low speed low torque region. And then when including, and then left is the FEM, pure FEM result, and then the right is the lookup table with high frequency iron loss. And then when we consider this high frequency iron loss, this JMAG result can match with FEA quite well. Similarly, other operating points, when we compare the iron loss between the FEM and the JMAG with high frequency iron losses, at any operating point, it shows us that quite a good matching.
So I guess, Yoko, I have a question here is you mentioned about we can measuring different operating points under this torque speed data, and you say the FEM data can quite nicely match with the lookup table with high frequency losses. What's the reason behind?
Yeah. So the reason this lookup table solution can match with FEA, considering the FEA is a reference, is that mainly because this lookup table solution with high frequency iron loss is considering that iron loss due to the switching frequency. So as it can consider that the losses are coming from the switching on and off behavior, we can also explore that how the switching frequency affects the machine iron losses. So, for example, here, this additional chart tries to show that case study of the 4 different switching frequencies from the 5 kHz to 20 kHz. And then you see that the 20 kHz show that the lowest iron loss. This is because that the current ripples can go down when we use that higher switching frequency. And then along with that this ripple down in that current, the iron loss goes down. Therefore, we see that lowest iron losses when we use that 20 kHz switching frequency. The point of this chart is we do this study using the MATLAB Simulink Simscape. So using that the system level simulation tool, we can investigate how that iron loss will be affected by the inverter's specification.
I see, that makes sense. Yeah.
Okay, so that was a little bit of the chat about the iron losses, and then here's a summary of the our discussion today. There are 3 Simulink blocks available to connect JMRT and MATLAB Simulink Simscape. First is that FEM parameterized block, and then this block can consider saturation, torque ripple, and it has a simple iron loss modeling. And at interface, it covers the Simscape Electrical and mechanical interface. And this block is a native Simscape network model. Therefore, it is most computationally efficient. Second one is the JMAG RTS function block plus network coupler. So this model also, of course, can consider the saturation and torque ripple because it uses JMAG RT. And on top of that, it can consider the advanced iron loss modeling. And then this block also has a Simscape electrical mechanical interface. One downside, if I dare to talk about the disadvantage, is that operation the additional operation is required to connect the S function block and this network coupler block. So a little bit of that, like 3 minutes of that additional operation might be required. Then third block is a JMAG RTS function block with Simscape terminals. And this block can consider the saturation and torque ripple. And then, of course, that advanced iron loss modeling is considered because it is that from the JMAG native product. And then this block's downside is that it only has the Simscape electrical interface. So when you want to connect with the Simscape mechanical library, you may need to implement by yourself a little bit. But there's an advantage. This one has a interface to the Simscape, so it can directly connect to the Simscape Electrical library block. Hey, that is a summary of this webinar.
Yeah, so I know we've been go through very quickly on the different framework that we can support in terms of integrating Simscape Electrical and JMAG RT block for motor control design simulation. But if you are interested to learn more about the demos and the presentation slides, feel free to reach out to us in our email, and we are happy to support you and talk to you offline. Thank you, everyone.
Thank you, everyone.